In this lecture, we're going to continue with discussing various tests for convergence of series. And the first one that we're going to discuss will be the ratio test, which actually turns out to be an immediate consequence of the root test. So first of all, let's state what the ratio test, actually remind you what the ratio test says. So if you have a series AN, then we have three possibilities. If lim sup as n goes to infinity of an plus 1 over an absolute value is going to be less than 1, then the series is going to converge absolutely. If lim nth now of the same quantity is bigger than 1, then the series is going to diverge or not converge. And in the only remaining case, when lim sup is greater or equal than 1 and lim nth is less or equal than 1, then the test is going to be inconclusive. So remember that in the root test, the quantity we worked with was lim sup of the nth root of absolute value of n. So and that determined everything. In this case, both lim sup and lim nth actually will play a role. And the most important thing in the proof of the ratio test is this result that we proved a few lectures ago. And this is the following, that if you take lim sup of an plus 1 over an, this is always going to be greater or equal than lim sup of the nth root of an. Lim sup of the nth root of an is automatically greater or equal than lim nth of nth root of an, because lim sup of something is always greater or equal than lim nth of the same quantity. And then lim nth of the nth root of an is going to be always bigger than lim nth of the ratio n plus 1 over n. All right, so then to prove part 1, let's suppose that lim sup of n plus 1 over n is less than 1. If that is the case, then this quantity is less than 1. And if this guy is less than 1, and everybody else here is going to be less than 1, because they're all less than lim sup of the ratio. So in particular, lim sup of the nth root of an is absolute value of nth root of absolute value of n. This is less than 1, and then from the root test, we know that this means that the series must converge absolutely. And so that's a conclusion, that's a proof of the first statement. Then the second statement, if lim nth of nth root, lim nth of an of n plus 1 over n is greater than 1, then this guy is greater than 1. And if he's greater than 1, then everybody else is going to be greater than 1. In particular, lim sup of nth root of an is greater than 1. And by the root test, that means that the series will either diverge or not converge. And I'm not going to prove number 3, but the way to do it is to do exactly the same thing as we did in the part 3 of the root test. You just show that for two examples, an equal to 1 over n and an equal to 1 over n squared, we're going to get that lim sup is greater or equal than 1 and lim nth is less or equal than 1. And so therefore, for both series, we are in the case number 3, but the series 1 over n diverges while the series of 1 over n squared converges. Again, for 1 over n squared, you just have to take, to believe me, that 1 over n squared, series of 1 over n squared converges, but we're going to shortly demonstrate that this is indeed the case. One important fact here is this, that This means that in order to demonstrate the ratio test, we use the root test. So that means that the root test is going to be somehow a weaker statement. It is possible that the root test.
Here's some information.
It is possible that the root test will give you, as we will see shortly, in fact, that it will give you, allow you to make some conclusion about the convergence of a series, while the ratio test will be inconclusive. And indeed, you can see this based on the following statement here that I'm writing on this page. So if lim sup of the nth root of n is equal to 1, right? So that means that the root test is inconclusive. Then from our famous result that we already referred to a bunch of times, from this result, what do we see? We see that lim sup is equal to 1. That means lim sup of nth root of n is equal to 1. That means that lim sup of an plus 1 over n is greater or equal than 1, and it means that lim nth of an plus 1 over n is going to be less or equal than 1. So if the root test is inconclusive, that the ratio test must be inconclusive, right? Because lim sup is greater or equal than 1, and lim nth is less or equal than 1. But the opposite is not necessarily true. It is possible that lim sup is greater or equal than 1 and lim nth is less or equal than 1, but that doesn't mean that this guy will have to be 1. It just has to lie between this number and that number, and it may or may not be equal to 1. And if it is not 1, then the root test is going to be conclusive. Okay, so let's actually, before I demonstrate, give you an example of what I just said, we are going to prove this corollary, which demonstrates that most of the time actually, or not most of the time, but a lot of times, root test and the ratio test actually are going to give you exactly the same set of predictions. And that is going to be true as long as the limit, not lim sup or lim nth, but the limit of n plus 1 over n exists and is equal to L. If it is equal to L, then we will see shortly that the limit of nth root of n is also going to exist and be equal to L. And so then if this guy is less than 1, that guy is less than 1, if this is equal to 1, this is equal to 1, and so on. Now, it's really easy to see that this statement follows from that statement. And again, we refer to the same set of inequalities. If the limit of an plus 1 over an exists, then we know if the limit exists, then lim sup of your sequence is the same thing as lim nth of your sequence. So if the limit of an plus 1 over n exists, then this and that is the same number. And if that is the case, so if this is equal to L and this is equal to L, then by the remaining inequalities, both lim sup and lim nth of the n is equal to L, and if lim sup and lim nth are equal to the same number, then your sequence converges to that number. And so that's basically our corollary here. Okay, so that means that if you use, for example, a ratio test, and you compute and the limit of an plus 1 over n exists, and let's say it is equal to some number, then there is no reason to do the ratio test, because the ratio test is going to tell you exactly the same thing. So for instance, if the ratio test is inconclusive, if the limit of an plus 1 or an is equal to 1, then there is no reason to use a root test because the limit in the root test is also going to be equal to 1. All right, so we'll come back to that in a moment. And in the meantime, let's look at this particular example, which will demonstrate the relationship between the ratio test and the root test. So let's suppose that we have a series in this form. It's going to be 2 to the power minus 1 to the power n minus n. So the power of 2 in this case is somewhat complicated. And I want to determine if this series converges or not. And I'm going to try both ratio and the root test, and I want to see what sort of thing they will tell us. All right, so for the ratio test, I will need to know things like lim sup and lim nth of an plus 1 over an. So an plus 1, an is this expression. An plus 1 is going to be the same thing, except that n is replaced by n plus 1. So then the top is 2 to some power, bottom is going to be 2 to some power. So if I take a ratio, then it's 2 to the power, which is a difference of powers on the top and powers on the bottom. So it's minus 1 to the n plus 1 minus 1 to the n, minus n plus 1 from here, and then minus n plus n from the bottom. Then quickly we see that n's will cancel, right? This n and that n will cancel. And then minus 1 to the n is essentially minus 1 to the n times minus 1. So this would be minus 1 to the n plus 1. And I already have 1 minus 1 to the n plus 1 up here. So at the end of the day, the power is going to look like twice minus 1 to the power n plus 1. And from this term, minus 1 remaining. So this is that. Now, before I compute lim sup, let's see how this sequence actually looks like. The first term is going to be 2 to the power minus 1 to the power, let's see, we're starting from 0, so to the power 0 plus 1, minus 1 to the 1 is minus 1. So minus 2 minus 1 minus 3, so this will be 2 to the power minus 3. When n is equal to 1, we're raising minus 1 to the second power, it becomes 2, it becomes 1. So 2 times 1 minus 1, that's 1. So we get 2. And then the only way n appears here is as a power of minus 1. So if I use n odd, I will always get the same outcome, or if I use n even, I'll always get the same outcome. So for odd, I got 2 to the minus 3 for first one. So the third is 2 minus 3, fifth is going to be 2 minus 3, etc. Second is 2, fourth term is going to be, it's again an even term, so it's going to have 2 in it. And so then at every even position, we're going to get 2. And so now if I have an oscillating sequence like that, which oscillates between 2 to the minus 3, which is 1/8, and 2, then lim sup, of course, is going to be equal to 2, and lim nth is going to be equal to 1/8. So we have this lim sup, this lim nth. 2 is greater than 1, 1/8 is less than 1, so we get that the ratio test is inconclusive because lim sup of the ratio is bigger than 1 and lim nth of the ratio is smaller than 1. Okay, so let's try to use a root test instead. So now I'm going to take exactly the same quantity, take the nth root of it, and take a limit, take lim sup of it. So if I raise 2 to 1 power and then another power 1 over n, then this is 2 to the power product of powers. So if I distribute n, this is what I'm going to get. And when n goes to infinity, minus 1 to the n over n, this goes to 0. So in fact, not just lim sup, but the limit in this case is going to be equal to 1/2, right? Because it's going to be 2 to the power minus 1. And 1/2 is less than 1. And so the root test then is conclusive. And it shows that the series must be absolutely complete. And this actually is an example of the case when not just the lim sup, but the limit in the root test exists, but nevertheless the limit in the ratio test does not, right? What did we say up here? So again, if I look at this chain of inequalities, if lim sup of the ratio is equal to lim inf of the ratio, then the limit of the root must exist. But if these two guys are equal, if the limit of the root exists, then it doesn't tell me anything about the limit of the ratio. Then lim sup does not have to be equal to limit. And that's precisely the situation in which we found ourselves in this latest example. All right. And now let's do a few more examples of the ratio and the root test. In fact, of all tests that we have learned so far. And let's start with the series n plus 1 divided by 3n minus 2. If you need to choose a test for convergence, you should start with the easiest one. And the easiest one is actually a test for divergence, which requires you only to find the limit of the sequence and determine if that limit is 0 or not. If the limit is 0, then the test doesn't tell you anything. But if the limit is not 0, then this guarantees that the series is not going to converge. And in fact, in this case, if I take a limit of n plus 1 over 3n minus 2, so either we divide top and the bottom by highest power of n, or we just look at this expression and we try to analyze it. If n is big, then 1 on the top and minus 2 on the bottom will play lesser and lesser role, right? Eventually, if n is a million, then these 1 and 2 are not going to matter. And so then n plus 1 over 3n minus 2 is approximately n over 3n. You cancel n, you get 1/3, so the limit must be 1/3. 1/3 is not equal to 0, so it means that the series diverges by the divergence test. One other way to think about it is that if the limit of a sequence in this case is going to be 1/3, that means that eventually in the tail of my sequence, I'm going to keep adding 1/3 to itself infinitely many times, and that means that the series diverges to infinity. Now, what about if we replace 3n on the bottom by 3n squared? Would this series converge? Let's try the divergence test again. So on the top, I have n plus 1, on the bottom 3n squared minus 2. So again, in the previous case, I argued that 1 and minus 2 do not matter. I can do that here as well, or I can just be more precise and divide top and the bottom by the highest power of n, which in this case is n squared. So n over n squared is 1 over n that goes to 0, 1 over n squared goes to 0, 2 over n squared goes to 0. So top goes to 0, bottom goes to 3. So the limit is equal to 0, and that means that the divergence test is inconclusive. It only works if the limit is not equal to 0. All right, so if divergence test is inconclusive, what else do I have? I have root test, I have ratio test, and I have comparison test at this point. So let's try the ratio test. This is the nth term of my series. This is the n plus first term of my series. I divide n plus first by n plus first term by nth term. I can remove the absolute value sign because when n is big, the only thing that can be negative here is denominator, but in fact for all n greater or equal to 1, the denominator is a positive number. So when I take a limit, when I deal with large n's, everything here is positive. So again, this is a ratio of powers of n. If I look on the top, when I add 2 to n, then 2 really is unimportant. When I subtract 2 from 3n squared, 2 is unimportant. 1 is unimportant. And compared to 3n squared, 6n and 1 are really small, so I can ignore them as well. So this limit must be the same as the limit of this quantity, which gives me 1. So the limit of the n plus first term over the nth term is exactly 1, not lim sup or lim nth, but the limit. And so then if a limit of the ratio exists, then the limit of the root would exist and be the same thing. So for the root test, I'm also going to get 1. So that means that both the root test and the ratio test are going to be inconclusive. So the only thing that remains then is a comparison test, and let's see if we can say something by using comparison. Again, the motivation, in order to use a comparison test, I need to find another series for which I know if it converges or not. And the series should be larger or smaller than the series that I have to determine convergence of. And so let's see how this series again behaves when n is big. When n is big, 1 and minus 2 are not going to be very important. So I can try to drop 1 and minus 2. Or when n is big, then what I see is essentially n over 3n squared. And if I cancel n, this is 1 over 3n. And what do I know about the series 1 over 3n? That's basically the same kind of a series as 1 over n, except that you have an extra factor of 1/3. So that series is like a harmonic series, so it should diverge. So if it is then, if my series eventually looks like a divergent series, 1 over 3n, then I can try to compare if my series is related to 1 over 3n in any way, and in what way do I want them to be related. If I want to prove that my series diverges, because it can be compared to another series that diverges, then my series has to be bigger than the divergent series to which I am comparing it, right? Because if it is bigger than a series that the sum of which goes to infinity, then the sum of my series also should go to infinity. And so let's see, in this case, if I take n plus 1 over 3n squared minus 2, if I remove 1 from the numerator, then I'm going to get an expression which is smaller. If I remove minus 2 from the denominator, I'm going to make the denominator bigger, so the ratio will become smaller. And n over 3n squared, I can cancel 1 of the n's, and this will give me 1 over 3n. So 1 over 3n is a divergent series, so my series is term-wise bigger than 1 over 3n, so then it must diverge as well. Now, regarding our use of root and the ratio test for this particular example, we saw that both tests were inconclusive. And in fact, it turns out that this is always going to be true if an is a rational function, so it's a ratio of polynomials in terms of n, one polynomial on the top, one polynomial on the bottom. Then in a case like this, ratio root test will never be conclusive because the limit is always going to be equal to 1. And in fact, the same is true for algebraic functions that also involve radicals. So in those cases, it's pointless to use ratio root test for example, in a test, because you are going to just waste your time to find something which is going to be useless. So you have to use other tests for rational functions and such. So in particular, you see that the comparison test worked pretty well there. All right, so next example, does a series 1/5 to the n converge? This one is really simple, because here you just have to recognize that what you're looking at is a geometric series. And it is a geometric series with a multiplier 1/5, which is less than 1. So that means that this series has to converge. In fact, it's pretty easy to, although unnecessary, but it's pretty easy to see that the series converges also by a root test, because how the root test work, I'll have to take nth root of 1/5 to the n, which is 1/5, limit of 1/5 when n goes to infinity is 1/5, and that certainly is less than 1. But again, everything is going to be much easier if you just recognize that you're dealing with a geometric series. All right, so now what if I have a similar series, but now it's n times 1/5 to the n. So now this is no longer a geometric series, because it's not just the sum of powers of the same number. And so in this case, you can try to use a ratio test or a root test for that matter, but let's use a ratio test. We need to take a limit of the n plus first term divided by the nth term. 1/5 to the n plus 1 divided by 1/5 to the n is just 1/5, which I can pull out of the limit. And then what is left is n plus 1 over n. And the limit as n goes to infinity of n plus 1 over n is 1, again, because when n is big, 1 on the top really makes no difference. So limit is 1/5. So then the series up here still converges absolutely. Even though I'm multiplying 1/5 to the n by a fairly large number, n, eventually, right, which is not bounded. But 1/5 to the n goes to 0 much faster than n goes to infinity, and that means that I'm still able to add up infinitely many terms of my series. And the last example here, you'll have to do many more examples from the corresponding section of a book, is going to be also something which kind of looks like a geometric series, except that now I'm dividing it by n factorial. Just to remind you, n factorial is a product of all integers between 1 and n. And so I'm trying to see if the series converges. And again, I'm going to use the ratio test. So the n plus first term is this. 1 over nth term is that. Everything here is positive, so I don't need to take the absolute value. Then I see this is 3 to the power n plus 1. This is 3 to the power n. I can cancel 3 to the power n. I'll have an extra 3 on the top. N factorial is a product of all integers up to n. N plus 1 factorial is a product of all integers, positive integers, up to n plus 1. So that means that all terms in this product are also in that product, except that the bottom product will have 1 extra n plus 1. And so then if I simplify everything, I only have 3 over n plus 1 left. And as n goes to infinity, 3 over n plus 1 goes to 0. That is less than 1, so the series must converge by the ratio test. All right, and so next time we're going to look at yet the next test for convergence.